Hi there, how's it going? In this lab, I'm going to show you how to control an IoT device by using Node-RED app and IBM Cloud. Here's the outline of this video. First, I will briefly explain the objective of this lab. Second, I will quickly go over the system structure and the major components that we're going to work on. Then I'm going to give you a live demo. After that, I will show you the entire procedure. Here's the lab objective. In this lab, we're going to build an IoT system in which a particle photon connects a sensor, reads and publishes the sensor's reading to a cloud. We're going to use the IBM Cloud in this lab. A Node-RED app running on IBM Cloud subscribes, receives, and processes the sensor readings. It will automatically trigger an alert tweet if the sensor data meet certain conditions. In addition, it will also automatically generate a control command and send it back to particle photon. The particle photon subscribes, receives the control command, and take certain actions accordingly. For example, to spin a DC brushed motor faster or slower, drive a DC servo or stepper motor to different positions. Here's a very simplified diagram showing the system overall structure. Basically, it has three layers: local, cloud, and the end user. In the local, we're going to use the particle photon to connect sensors and actuators. On the cloud, we're going to use IBM Watson IoT platform and Node-RED app, which are the two services we're going to use on IBM Cloud. For the end user, we're going to send them the alert tweets. In this slide, I have a detailed diagram to show the detailed system structure. In the local, the particle photon connects a sensor and an actuator like a DC servo motor that I'm going to use for the live demo. Of course, it can be some other types of actuators used for your own projects. The particle photon reads the sensor's measurements and publishes the sensor's readings to the cloud. On the cloud, we use IBM Watson IoT platform to register and manage the IoT device. The Watson IoT platform also plays the role of a MQTT broker. On top of that, we're going to create a Node-RED app running on IBM Cloud to subscribe and receive the sensor's readings through the MQTT broker. If the sensor reading is greater or smaller than certain threshold, it will automatically trigger a alert tweets and send it to the end user. In addition, the Node-RED app will automatically generate a control command and publish back to Photon through the MQTT broker. The particle photon subscribes and receives the control command and takes certain actions according to the received commands. In this lab, we're going to let the Node-RED app automatically generate the control command. Of course, you can configure your own Node-RED flow to let the end user to initiate the control command and send it back to the photon through the MQTT broker. Here's the major components that we're going to work on for this lab. For the local particle photon, we need to program it to publish sensor data, subscribe, receive, and respond to the control commands. On the cloud, we need to register manage the IoT device. As an optional work, You can use the visualization boards and cards on IBM Watson IT platform to visualize the sensor data. Third, we need to create a loader radar app to subscribe the sensor's readings, compare the data with predefined thresholds, trigger Twitter alerts, and generate and send the control commands back to Photon. By the way, here is the major components for the previous Lab 7. You can find Lab 7's video through the link below. Over there, we just needed to program the IoT device particle photon to publish sensor data on the cloud. We just needed to register and manage the IoT device and create a loader radar app to subscribe the sensor data, compare the data with predefined threshold, and trigger the Twitter alerts. So compared to Lab 7, for this current lab, we just need to add two major components here. One is to program the particle photon to subscribe, receive, and respond to control commands. For the loader radar app, we need to add the words. We need to expand the flow to generate and send the control commands back to the particle photon. Now let me give you the live demo. Before I start, let me turn on the camera on my laptop, then you can see what I have in front of me. I have the finished circuit here. Here's the particle photon. The red color board right under the particle photon here is a battery extension board made by SparkFun. By using this battery extension board, you can use an external power supply or a battery like this Li-ion battery pack here to power up photon. Here's a potentiometer which is used to mimic an actual sensor, like this temperature, humidity, DHT22 sensor. The issue with using an actual sensor is that it may not give you a reading you want in order to trigger the alert and the associated control commands. Instead, by using a potentiometer, you can just simply adjust the potentiometer's position here and get a reading to trigger the alert and control commands anytime you want. You flash the coding into the board. The code should start running any second. Here we go. Yes, we see this blue colored LED blinks. That means data is published to the cloud, and this yellow colored LED blinks that indicates a control command is successfully received by a particle photon. And I bet right now the control command is turn no, so this green color LED blinks. For this first demo here, the control command is a string tap, and let me go back to the cloud and take a look what a control command is being sent, and let's verify that, and then we move on to the second demo. And right now 0 is being sent to the cloud, and then a turn no control command is published from the cloud and received by the photon. And then let me open up the loader radar app. Here we go. Alright, that's the first demo in which the Node-RED app generates a string type of command to control the particle photon. The issue with a string type of command is it has a very limited capability to pass on multiple control parameters. For example, if you want control the servo motor to stay at a certain position for a certain period of time, the string type of command cannot do that. So a better option is to use a JSON format control command, which is the second demo I'm going to show you. Let me disconnect the USB cable and power off the photon and set up everything. I'm going to add up the servo motor into the circuit, and let me fire up another Node-RED app I have already created for the second demo. This is a separate Node-RED app I have already created specifically to generate JSON format control commands. Okay, right here. Okay, it's turned on, and then let me flash the code I have already written for the particle photon to receive and respond to the JSON commands. Okay, the code is successfully flashed, and let me open on the camera for you, and then you can see what I have here. I have the servo motor connected already. Let me restart the code from the very beginning again. Okay, that's the initialization. Sweep the servo motor a little bit to initialize. And right now it's in the nominal position, the 90 degree. And here we go. We have the blue colored LED blinks that indicates a data being published by the particle photon to the cloud, and the yellow colored LED blink that indicates a turn no control command is being received. And then the servo motor moves to a lower position, which is 0 degree. Here you go, and stay there for a few seconds, and then resume back to the nominal position, the 90 degree. That's turn no control command. A JSON formatted control command is generated by the Node-RED, which includes a time duration specification, and then the servo motor can follow the control command and then keep the position, the lower position, for certain seconds. And then right now, I guess the sensor data, the dummy data published by the particle is not in the any range to trigger the control command. So here we go. We have the red colored LED blinks. That means a high control, turn high control command is being generated and received by the particle photon. And then look, the servo motor moves to the high position and stay there for a few seconds. And then let me open up the serial communication between the host computer and my photon. You can see what is the exact control command. And here we go. We have 80 dummy data being published to the cloud, and turn high control command being generated by the Node-RED app, and the particle photon received, and move the servo motor to a high position and stay there for 3000 milliseconds. And we have 90 being sent to the cloud, and the turn high being triggered and being received, and then remain there for 3 seconds, and 100, and then we have turn high, and then right now 0, and then the servo motor should move to the low position, which is 0 degree, and stay there for 5 seconds. After 5 seconds, goes back to the nominal position, which is a 90 degree. And here we go, we have another turn node command being received, and the servo motor moves to no degree, 0 degree, low position, and then stay there for 5 seconds, and then goes back to nominal position. Here we go, we have another turn node command come in, and the LED blinks correspondingly. Publish, receive the control command, and the servo motor moves low position and stay there for 5 seconds, and then resume back to the nominal position. Here we go, perfect match, works perfectly. And then right now the dummy data is 40, and no any control command is being triggered. Alright, that's the second demo. I think it works perfectly as what we planned. Okay, let's get back to the procedure. The entire procedure has about 20 steps, but please be noted the first 16 steps are the same as previous Lab 7, so you can refer to Lab 7 video for details. The video is posted on YouTube, and the link is right here. You can also find this link in the description right below. To save time, I'm gonna just read the steps here to you. Step 1. Log into IBM Cloud and launch Watson IoT platforms. Step 2. Create a device tab on IBM Watson IoT platform. Step 3. Register a device ID on IBM Watson IoT platform. Step 4. Change connection security setting on Watson IoT platform. Step 5. Build a circuit to connect a potentiometer with particle photon. Double check the circuit. Connect photon to a host computer. For proof of concept, you can just use a potentiometer instead of an actual sensor for manually activate the Twitter alert message anytime you want. Step 6. Log into Particle Online ID. Verify photon's internet connection. Use the registered device credential information and program the photon to publish sensors reading to IBM Cloud. You can refer to my example code for Lab 6, which has been posted on CityTech Robotics Research Lab's website. Here's the link. Another tip here is take notes about the event ID and the data property used in your code, because they will be needed later by IBM Cloud. Step 7. Go back to Watson IoT platform to create a board and a card to visualize the sensor data. Note, when you set up Connect dataset for your visualization card, make sure that event and property fields exactly match what you are using in your photons code. Step 8. Open your IBM Cloud dashboard, open Catalog software, launch Node-RED app service, create a Node-RED app. Note, during this step, you will also create a Cloudent service, a secret store service, or developer toolchain instance. You can save your Node-RED app's API key on IBM Cloud by using secret store service. Step 9. Connect the newly created Node-RED app with the Watson IoT Platform Service instance, where you used to register your IoT device. Make sure verify the status of your IoT Platform Service instance is active. Note both your IoT device, which is the particle photon, and the Node-RED app are MQTT clients. The MQTT broker is IBM Watson IoT platform. Step 10. Start the Node-RED app editor on IBM Cloud. Note, right after the username and the password just been created, attempt the first time logging to the editor may fail, so you can just simply wait for a little bit while and try it again. If the username and the password to log into the Node-RED app editor are lost, you can manually reconfigure them by setting Node-RED username and Node-RED password, these two environment variables, on the app's runtime status page. Step 11. Make yourself familiar with the Node-RED editor's GUI and the features. Create a Node-RED flow. You can refer to my example Node-RED flow posted on CityTech Robotics Research Lab website. Step 12. Replace the IBM IoT node in my example flow by MQTT in node. Set up correctly. Here I have detailed instruction showing you how to set up the MQTT in node. You have to set up the server, client ID, username, password, topic for the MQTT in node. That node is extremely important. You have to be very careful when you set this one up. For details, you can refer to previous Lab 7 videos for details. Next step, step 13. Log into Twitter. Go to developer.twitter.com to apply for a Twitter developer account if you don't have one yet. Note, access to standard API is good enough for most cases. Yes, you need to answer all those required questions when apply for a developer account with Twitter. Most time your application will be approved quickly. If you have an academic email address, select academic for the primary reason for using Twitter developer tools. Then your application may get approved instantly. Step 14. Log into your Twitter developer account. Create a new Twitter app. On the app page, use your Node-RED app's URL for website URL and callback URLs. Be careful to keep a record of your Twitter app's API and API secret key, API token and access token secret, because all this credential information will be needed by the Node-RED app. Step 15. Go back to Node-RED editor, install Twitter node, insert a Twitter out node into the flow. Correctly set up. Use your Twitter app's credential information to set up Twitter out node. Namely, you have to put in API key, API secret key, its access token, and access token secret into that node to set up. And then that Twitter out node can smoothly communicate with your Twitter app. Step 16. Run particle photons code, view data visualization in board card on IBM Watson IoT platform, view Twitter alert message being posted on your Twitter page. You can use a serial communication tool such as PuTTY or Terraterm in Windows, Screen in Linux and Mac OS to view and verify the data actually being sent out from Photon. By here, all these 16 steps are the same as previous lab 7. Again, you can go view lab 7 video on YouTube to see the details. The video's link is posted right below. And let's start from here are the new steps we have to add on based on the previous lab. Step 17. Update node-RED flow to generate and send commands. Go to load-RED flow editor. From the load palette, drag and drop function node into the existing flow. Edit the nodes to generate control commands. You can refer to my example flow posted on CityTech Robotics Research Lab website. I suggest you try string typed command first and then JSON formatting later. You also need to drag and drop or MQTT out node into the flow and then set up correctly. The way to set that node up is very similar to MQTT in node. How to set the MQTT in node's topic property? You can set up as this. And here let me show you how we finish this step. First of all, go to CityTech Robotics Research Lab. And open up the example flow, which I post here for lab 8. Lab 8, control remote device through node-RED and IBM Cloud. I wrote this example node-RED flow for sending commands to remote devices. Click it, open up, copy paste, and put it into your node-RED app. The MQTT in node is for the entire node-RED app to subscribe and receive sensors reading through MQTT broker. The MQTT out node is for the node-RED app to publish the control commands to the MQTT broker. And then later the particle photon can subscribe and receive the control commands through the broker. Here let me show you how to set up these two nodes. Let me start with the MQTT out node. the apps flow here. We can move on to the next step. Before we move on to the next step, here's one tip. For the MQTT out node here, do not use any wildcard for the topic property, but instead you can use wildcard for the MQTT in node's topic property, like the one we are using here. For the format, use the wildcard, which means that's something you should keep in mind. Alright, let's get back to slide and check out the next step. Step 18. Update Photon's code to subscribe, receive, and respond to string type commands. You can refer to my example code posted on CityTech Robotics Lab's website. I have one tip here. Make sure the command ID in the code match with the one used in MQTT outlaw of your Node-RED app, which we have already done. Another tip here is you can add LEDs into your circuit, write code to bring them as an indicator for publishing data and receiving commands. The example code is on the CityTech Robotics Lab's website under the Lab 8. I have this example code for Photon subscribing and responding to string commands from IBM Cloud. Click, open up, you can read about that's the example code. Actually, I have already copy paste this code into here. That's what we used before already. Alright, let's move on to the next step. If you want the Node-RED app to generate a JSON format command, of course, first thing we need to do is to modify the Node-RED app flow to generate a JSON format commands. Go back to the Node-RED app flow you created before, and we don't need to change that much here. The only thing we really need to change is to modify this function node. Instead of here generate a string type command, and then we have to replace this one by a JSON format command. I have the sample code here, so I just come out this one, and now we have this line of JavaScript code to generate a JSON format command. We have test command, that's the name of the field, and then the actual value here is turn null. It's very simple. By using this line of code, your MQTT payload will have a JSON format control command, and then just return this message. Okay, very straightforward. For the other function node, we can do the same thing. Command out the string type of command, and then use this one to generate a JSON format command. And then done. We finished the Node-RED apps updates, and you can deploy it. And then let's take a look at what we need to do next. We finished the Node-RED apps, and then we need to modify the Photon's code. You can refer to my another example code posted online. IoT course page located on CityTech Robotics website. Locate the example code, which is for Lab 8. Here's the example code you can refer to. But please pay attention to the date of the last update. I was using a library called Arduino JSON to parse the receive control command. This library might be updated lately, so you need to check it out whether and how you needed to update this code. Rewrite my example code to use updated Arduino JSON function to receive and parse JSON formatted commands. Search and refer to the official documentation for tech details. Here's the link of the official Arduino JSON website. Let me show you how to do that. Specifically, in this example code, I was using JSON buffer to store the received JSON formatted control commands. If you check out the Arduino JSON official website, here's the site. You will find how to update the JSON buffer. That's the first line you need to update here. Another part of the code you need to update is this parse object function. That was the function used by the library to parse the received JSON control commands. Go read the official documentation of Arduino JSON. You will find out how to update that function. Alright, it's quite straightforward. I have the updated code here. They already replaced the JSON buffer by JSON document. I will also already replace the parse object by deserialized JSON. That's how you parse the received control commands. Pretty much that's it. And over here you need to update your code to extract the actual value from the JSON control commands. We're done with the code. I have a tip here: make sure the control command ID in your code match with the one used in MQTT out node of your node-related apps flow, which we have already done. Let's move on to the next step. Step 20. Verify Photon's code. Correct any error if there is. Flash and run the code on Photon. Adjust potentiometer's position. You should see the expected movement of your motor and LED indicators if you have one. You can use a serial communication tool, PuTTY, table term, or screen to view the actual data being published from Photon. You can view and verify data visualization on IBM Watson IoT platform. View and verify debug message in the debug view of your node-related apps editor. You can also view the alert tweets posted on your Twitter. Let's give it a run. Everything right now should be up running correctly. Okay, here we go. The code starts running in the particle photon, and it's connected to IBM Watson IoT platform and starts send the data to the cloud. 0 is just being sent, and then immediately a turn now control command is generated on the cloud and sent back to the particle photon. Particle photon receive it and remains at the null position for 5 seconds, and another number 10 being sent to the cloud, and then cloud generate a terminal control command sent back to the particle photon. Particle photon goes to the lower position, which is 0 degree, and it remains there for another 5 seconds. looks good. Let's go to the cloud. Here's the visualization card on IBM Watson IoT platform, and then we can see 4050 just received by the Watson IoT platform. And let's go to the loader rate app. Here we have 40, 50, 60 being received just a moment ago, and start from all the way 0, and then 10, and then 20. Okay, and let's get back to the Photon. Here we go. We have 70 just published from Photon to the cloud, and then cloud immediately generated a turn high control command, and then server motor goes to the high position, which is 180 degree, and then remains there for 3 seconds. Works perfectly. Put everything together, you can see we have 100 just published to the cloud, and then 0 coming in. The node rate will generate turn no command, and yes, the particle photon receives the turn no, and goes to the lower position 0 degree, and it stays there for 5 seconds. Perfect. Everything works well, and pretty much that's it. And over here I have a troubleshooting checklist. You can take a look over there, and you can read the details of this troubleshooting checklist to help you identify any possible errors. Alright, pretty much that's it. Thank you for watching, and see you next time.